Lesson 8.2, circles and ellipses. We're going to emphasize ellipses in this lesson, basically working with writing equations or identifying parts of an ellipse when given an equation. The basic definition for an ellipse is the set of all points in a plane whose distance from two fixed points in the plane have a constant sum. Those 2 points they're referring to here are the foci of the ellipse. So we can see down below we have our ellipse represented by the blue, we have the center, we have the 2 foci. So now if we look at this image that kind of shows the idea of what the definition of an ellipse is showing, we have our 2 foci, the one here on the blue segment and the one on the red segment. At any point, if we take the sum of the red segment and the blue segment, that is going to be the same total length. Okay, and we go around and rotate. That's our basic definition for an ellipse. Next, we need to go through the basic equations for an ellipse that is centered at the origin. If you look at both of these equations, they're very similar. It's just depending on whether the x squared term comes first or the y squared term comes first. How we know which term comes first is based on the values in the denominator. The value of a is larger than the value of b, and we always put that term first. So if the value in the denominator that is larger corresponds to the x squared term, we put that first. If it corresponds to the y squared term, we put that first. And then you can see if our x squared term is first, our focal axis is going to be on the x-axis, and we have our expressions we can use for the foci and the vertices, and then the similar idea for if our y squared term is first. If our x squared term is first, referring to the value of a being larger, that just means our graph, our ellipse, is elongated on the x-axis. So in this case, if we look at this graph, this would be an equation where the x squared term came first. The value in the denominator was larger on the x squared term. It's elongated on the x-axis. If our y squared term comes first, it's elongated on the y-axis, which we could see by this graph. First example, we want to find the vertices and the foci of the ellipse 9x squared plus 4y squared equal to 36. The first thing we need to do is divide by 36 so that the constant we're equal to is a value of 1. When we do that, we get x squared over 4 plus y squared over 9 equal to 1. We can see our larger value in the denominator corresponds to the y squared term, so we're going to write that term first. And then we're going to also write the denominator so that there's some value squared. So our new equation is going to be y squared divided by 3 squared plus x squared divided by 2 squared equal to 1. Now we're in a form we can go back to the table and use that table to identify the vertices and the foci. So now that we want to find the vertices and the foci, using our table, we know the vertices are going to be at the ordered pairs 0, plus or minus a. So we need to determine the value of a. Looking at our first term, we can see in the denominator that a value is going to be 3. So our 2 vertices are going to be 0, negative 3, and 0, positive 3. Now to find the ordered pairs for the foci, the value of c is not directly in the equation. We have to do the Pythagorean theorem essentially to find that value of c. Notationally, the Pythagorean relationship we have to use is in the form a squared equal to b squared plus c squared. Okay, not normally what we would have it. That's the way they have it set up in this textbook, so that's what we're going to use. So we know the value of a is 3. So 3 squared is going to be 9, equal to our value of b we can see is 2. So 2 squared is equal to 4 plus c squared. So now if we subtracted 4 to the other side, we would get 5 equal to, if we want to get c by itself, we have to take the square root. So we get c is equal to plus or minus 5, which means the ordered pairs over here are going to be 0, negative radical 5 and 0, positive radical 5. In this example, we want to find an equation of the ellipse with foci at -2, 0 and 2, 0, whose minor axis has a length 2. So using our table of values, we know the foci are going to be at plus or minus c, 0. We know it's in this form because it's the x values that change, not the y values in these ordered pairs. We also need to find the value of the semi-minor axis because we know that represents the value of b. If we're given the length of the minor axis, what we have to do to find the semi-minor axis is just divide that value by 2. So the ordered pairs for the foci are going to be plus or minus 2, 0. And for the semi-minor axis, the value of b is going to be 2 divided by 2. So we get a value of 1. Next, we would have to use the Pythagorean relationship to find the value of a. So we set a squared equal to b squared plus c squared, fill in the values we know. Now we get a squared is equal to 5. So we know what our value of a is, know what the value of b is. Now we can plug it into our standard form for this equation. Now the standard form for our equation is going to be x squared over 5 plus y squared over 1 equal to 1. Now we're going to discuss ellipses that are not centered at the origin. So we have our two conditions based on whether our value of a corresponds to the x or y value. And then we can see our expressions for the focal axis, foci, vertices, semi-major axis, semi-minor axis, and then the Pythagorean relationship. Here's a couple pictures that show the relationship between the center of the ellipse, the two foci, and then the two vertices of the ellipse. We can see we have our semi-minor axis that goes from the center to this point, and then we have the semi-major axis which goes from the center to one of the vertices. And then the same idea if the a value corresponded to the y term. In this example, we want to find the standard form of the equation for the ellipse whose minor axis has endpoints -1, 4 and 5, 4, and whose major axis has length 8. Off to the right, we have this picture that shows the information we have. We have the endpoints of the minor axis, -1, 4 and 5, 4. And we have the length of the major axis, which is going to go through the center of the ellipse, which we know is going to be the midpoint of -1, 4 and 5, 4. We also, from this information, know our general equation is going to be in the form y minus k corresponding to our a value because our major axis corresponds to the y-axis. From this information, we can identify the center of the ellipse. We can also identify the length of the semi-minor axis, which is from the center to one of these endpoints, and we can identify the length of the semi-major axis, which goes from the center to one of our vertices here. So we can identify the center is at the ordered pair 2, 4. The semi-minor axis going from the center to this point is going to be a distance of 3. And the semi-major axis going from the center to one of our vertices is a length of 4. Now we just have to take these values and plug them into our standard equation. Thus, the final equation we get is y minus 4 quantity squared divided by 16 plus x minus 2 quantity squared divided by 9 equal to 1. In this last example, we want to find the center, vertices, and foci of the ellipse, x plus 1 quantity squared divided by 4 plus y minus 1 quantity squared divided by 9 equal to 1. First thing we need to do is write down the information we know. We know the center of this ellipse is going to be at the ordered pair -1, 1. We also know the semi-major axis is going to correspond to the y-axis because our value of a corresponds to our y term. So we know h is equal to -1, k is equal to 1. Our a value, if we want to think of this as 3 squared, is going to be 3. And our b value is, if we think of this as 2 squared, our b value is going to be 2. So now we know the expressions for our vertices are going to be h, k plus or minus a, and the ordered pairs for the foci are going to be h, k plus or minus c. So a lot of this information we already have. What we need to determine is the value of C so that we can find the ordered pairs for the foci. Using the Pythagorean relationship, we can determine that the value of C is going to be equal to plus or minus radical 5. Now we just have to plug that into the expression to find the foci, and we already have the values we need to find the ordered pairs for the vertices. So for the center of this ellipse, we know it's at the ordered pair negative 1, 1. The vertices are at negative 1, 4 and negative 1, negative 2, and the foci are at negative 1, comma 1 plus radical 5 and at negative 1, comma 1 minus radical 5. One application often referred to when talking about ellipses is the orbit of objects in our solar system. So that is something we will discuss together in class. The last thing we need to discuss is eccentricity of an ellipse. So the basic thing I would want you to write down is this equation that we can refer to. The eccentricity of an ellipse is going to be E equals C divided by A, or the square root of A squared minus B squared divided by A.